right, let's get started. So today is circular motion and inertia, moments of inertia. And so I want to talk about circular motion again. So here I have a circle, has a radius r, and I have an object that's going to be moving around the circle. Now we already talked about a little bit about circular motion. What did we talk about before? You guys remember? That thing? Which was? Centripetal force. Okay. And so there's a force pulling it to keep it into circular motion. We talked about that, or centripetal acceleration. But now we're going to generalize this into motion where it can actually be not just moving at a constant speed around the circle, but it could be accelerating. And so we have these linear variables like position, velocity, acceleration, and we know that position goes to theta in circular motion, which is s over r, where s is the distance around the circle and r is the radius. Velocity now goes to omega. It's a Greek letter omega, it's not a W. Omega is the angular velocity, and it's also equal to the change in theta over the change in x, or change in t, change in time. So it's analogous definition to velocity, which is the change in x over change in time. It also happens to be equal to v over r. And so then the angular acceleration alpha is the change in omega over the change in time, which is also the acceleration over r. So we're sort of just dividing out everything by r in circular motion. Any questions so far? All right, so we talked about force too. And what's the law that we use to determine accelerations using force? Yeah, mass equals acceleration. This is Newton's second law. We've used it almost every single lab, I think. So there's an analogous rotational force that we call torque. And torque is equal to I alpha. What's alpha? It's this guy, which we call the angular acceleration. So this is sort of like an angular force. We call it torque. This is the angular acceleration. What's this? This I. No, it's not current, but good guess. We call it the moment of inertia. It's sort of analogous to the mass. So if you're looking at this equation, comparing everything, this is sort of like a force. This guy's sort of like a mass. This guy's sort of like a acceleration. All right, torque also happens to be equal to r crossed f, where f is the force and r is the distance. What does the cross mean? Have you guys seen this before? Cross products? All right, so whenever you see a cross product, you should think, if you look really hard at it, you look really close, you should see a sine theta in there. Can you see it? No? All right, so that's my joke for the day. So A cross B is equal to the magnitude of A. I'm running out of space. The magnitude of B, sine the angle between them. So you put a little sign there. All right, in mass, we already talked about this moment of inertia, I, and that happens to be equal to this formula. So it has mass in it, but it also has the radius in it, squared. And last week we talked about momentum. Momentum is equal to, help me out. mv, right? Mass times velocity. So we have an angular momentum, which we call L, and it's equal to, can we guess what it is? This is mv. What's our angular momentum? What's analogous to m in rotation? I, moment of inertia. What's analogous to the velocity? Omega. also is equal to r cross p. Where again, this is the cross product. So it adds a little sine theta in there. Any questions about this? So the point is, if you're really good at linear stuff, which you guys practiced the first, 3 or 4 weeks of this term, you should be good at rotational stuff, because everywhere in an equation that you had x, now you have theta. Everywhere in an equation you had v, you have omega, so on and so forth. So it's all the same kinematics equations. You guys remember the 4 kinematics equations? It's the same equations. All right, so let's talk about moment of inertia. So you have some object here, and it has mass. And you're going to rotate it about some axis. So I picked sort of a random axis here, and I'm going to rotate it. And I want to know what its moment of inertia is. So there's a formula for it. It says, go r distance away, pick a little piece of the mass, and plug it into this formula. And then sum up all of them. So if you had this piece of mass, you had this distance, but maybe this piece of mass had a different distance, right? So you need to sum them all up. So you might have, mass 1, r1 squared plus mass 2, r2 squared, dot, 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 dot. Now you notice this is an object that has sort of a continuous mass to it, right? There's mass everywhere. And so if you are familiar with calculus, this formula will go to r squared dm, the integral of r squared dm. All right, so these are the definitions for moment of inertia. And they're used to calculate for different objects. So you can have different shapes rotating around different axes. And one of the things I want to point out is that if you wanted to have a really small moment of inertia, how would you distribute the mass? Really close to your axis of rotation. Because the smaller r is, the smaller, right? So you're designing something, and it has a certain mass. It has to have 1 kilogram of mass. But you want its moment of inertia to be small, because you want it to be easy to rotate. So what do? You put all the mass as close as you possibly can to the axis of rotation. So bicycle wheels, do they have a small moment of inertia or a rather large moment of inertia? What do you think? Large, yeah, because most of their mass, because of the way they designed the spokes, is all out on the outside. Okay. All right, so for certain objects, we have the moment of inertia already calculated for you. A disk is 1/2 mr squared. Okay, I changed the notation a little bit. I made big M and big R. All right, that's because I'm going to use little mass later for something else, okay? So it's the same mass here, except that I'm going to call little mass something else later, so I changed it to big M and big R. A ring has mass on the outside, but it's taken away some of the mass on the inside, and it's equal to 1/2 m r1 squared plus r2 squared. Disk on its side. So now it's rotating about this axis here. So this is a disk and this is a disk. What's the difference between these two disks is that they rotate around different axes. This guy's about its center here. This guy's about its side. Which one do you think will have, if they have the same mass, will have a higher moment of inertia? This one or this one? All right, this one will. Why? Because its mass is further out than this guy's mass. More of its mass is closer to the center. And so its formula is 1/4 mr squared plus 1/12 ml squared, where L is this thickness here. So you'll be using all three of these formulas. That's why I put them up on the board for you guys, so they're easy to reference. And so how are we going to do this? So we have an apparatus here. It has a disk on it. We're going to rotate the disk. And the thing we're trying to find is its moment of inertia. So what's a way to find the moment of inertia of this disk? You guys think of a way? So Could I weigh it and then measure its radius? Okay, is that one way to find the moment of inertia of a disk? Yeah, sure. We can find its mass and its radius, plug it into this formula, and we find its moment of inertia. That's one way. What's another way? The other way is to accelerate it, to spin it, and have it accelerate by having a hanging mass. So what's this hanging mass doing to the disk? It's applying a force to it, right? And that force applies a torque. And it's going to rotate it. And we can measure its acceleration using the photo gate. Okay, there it goes, finally. It's one of those things, whenever you demo in front of a class, it never works. All right, so up here I have the disk. I have this apparatus drawn. It's got a mass m, radius r. Now I'm calling this hanging mass little m. All right, so we know that this force here, force of gravity, is equal to mg. If we analyze this guy here, this system of this mass, what's the first thing we do when we analyze a system? Free body diagram. So identify all the forces. I identified a force. Is that the only force on this object? What other forces? Tension. Good. You guys are becoming experts, right? Is there any other forces? There might be friction, but we're going to say friction's small and neglect it here. But there could be friction. So let's say that's it for now. Those are the two main forces. Well, what do we do next? After we do the free body diagram, identify all the forces. Yeah, we do equations. Which equation? Newton's second law. Newton's second, which says, help me out. Yeah, so in this case, I'm only concerned really about the y direction because it's the only one that has forces. So yeah, normally these guys would be vectors, but we'll just assume this is for y. And we get what? mg minus t equals ma. This is like half credit on an exam. All right, I'm going to solve for the tension. Tension is equal to, can I do it? It's either m times g minus a or a minus g. Is that right? Did I do it right? I skipped like 2 steps of algebra. I think it's, is it right? Or is it a minus g? Is it? Is the other way? Is it right? Okay. I should have just done the 2 steps of algebra. We wouldn't have to guess, right? All right, so this is the tension of the string. And this tension is also pulling on this mass here, the same tension. All right, and one thing I want to point out is the place where it's pulling on the string, on the hanging mass, the string is pulling, is at this guy here. All right, so this is applying a torque here because it's a force times a distance, but this distance is a big R. We're going to call it little r. It's a couple centimeters. All right, a couple centimeters. So don't put big R there, otherwise you're going to get a huge percent error. So this is roughly, I don't know, 2 centimeters. You have to measure it. All right, and so torque says what? What is torque? Yeah, it's I times A, but torque is also R crossed F, where F here is our torque. I'm going to put torque. This is sine. So let me just write it like this. RT sine theta. What's the angle between the torque and the radius R? Yeah, they're 90, right? Because this is the radius, and it's always pulling at a 90-degree angle. So sine of 90 happens to be, sine of 90 is 1. So we can get rid of the sine. So torque is also equal to R times the tension. But we know the tension, and we know R. So this is R, M, G, and A. We know A too, right, because we're going to measure it with our photo gate. So we know the torque is R, M, G minus A. And we also know the torque is I alpha, so we can set these guys equal to each other. So I alpha is equal to R, M, G minus A. What are we trying to do in this experiment? What are we solving for? Inertia. There it is. So let's divide by alpha. Do we know alpha? Alpha happens to be equal to A over R. So if I put A over R here, I'll get an A down here and another R on top. And that's the formula we're going to use to experimentally find the moment of inertia. All right, we know R, we know M, we know G, we'll know A from the experiment. All right, what are we going to do when we do that? It's an A, this one? Acceleration. We're going to compare it to these formulas. Do percent error. Any questions? All right, you guys can get started.